Thanks, James. And yeah, thanks for the opportunity to talk. I'll just share my screen. That works. There we go. Can we all see that? So yeah, I guess as James said, I'm going to talk about these bordism groups to do with, I'll get to defining soon, and they have a connection with contact topology through these Stein filling obstructions I'll discuss. So yeah, I guess it's a bit of an overview of the talk. So I'll probably spend the first 20 to 25 minutes giving some background, just in case people haven't. I know there's a lot of like low dimensional people here, so people haven't seen this stuff before. I'll try and go over some of the background, and then yeah, I'll sort of introduce these U alpha-bordism groups and talk about their calculation via this Tom spectrum. And then I guess I'll talk a little bit about why we might care about these bordism groups, how they kind of arise, and this will lead to this link with contact topology about the Stein fillability of these almost contact manifolds. Oh, and feel free to ask questions at any time, just yell out, and I'm happy to build them as we go. All right, so I guess the beginning of the story is vector bundles. So roughly speaking, an n-dimensional vector bundle is this map, and it's roughly a collection of n-dimensional vector spaces which are parameterized by some base space. So I guess the sort of thing to have in mind is the tangent bundle of a manifold, a smooth manifold. You have your smooth manifold, and then at every point you have this tangent space, which is a vector space, and it sort of varies in a sort of smooth and continuous and smooth way along the manifold. And then I guess another example to have in mind, which isn't a tangent bundle, but it has the advantage of being pretty much the only one that I can draw, which is non-trivial, is this sort of Mobius strip. So here we have this base manifold being the circle, and you can either think of at each point you have either extend these out infinitely, or just think of these as open, being homomorphic to R. And we have this one-dimensional vector space at every point. And so the idea is, the property is that, locally this needs to be trivial. So you can take any sort of neighborhood and cut it and kind of untwist it. It's just a product. But globally, you can have this twisting, which you can't sort of untwist. Okay, and so these are just sort of your standard unoriented vector bundles, but you can add extra structure, so orientations, complex structure, spin structures, things like that. And the definition that we'll use for giving these structures, I guess there's a few different ways to do it, but we'll look at it via these classifying spaces. So what are classifying spaces? So classifying spaces are these spaces BON, which classify vector bundles in the sense that sort of equivalence classes of vector bundles, n-dimensional vector bundles over some base space B correspond to homotopy classes of maps from the base space into this classifying space. So you can think of it as representing a certain sort of functor here. And specifically, the way that we get this correspondence is if we have a map, say, from B to BON, well, over every classifying space, there's this universal bundle, gamma n, and there's a construction that you can do with vector bundles where you pull back. And so you just get a vector bundle over B by pulling back from this classifying, the universal bundle by this classifying map. I guess another kind of technical point, a lot of this talk we're going to be working stably. So, an n-dimensional vector bundle is classified by map to BON, but all of these have these kind of natural inclusions into each other, and you can sort of take the co-limit and think about this sort of stable classifying space, which classifies stable vector bundles, which basically means we're allowed to add on a sort of arbitrarily higher number of trivial bundles onto it. Okay, so G structures, so putting structures on vector bundles. If we have a map from, say, so now we're working stably here, this is the stable orthogonal group. If we have a map from some, say, topological group, G to the stable orthogonal group, then we define a stable G structure on a given bundle. So now we're really just, whenever we talk about bundles, pretty much we're going to be thinking of them by their classifying map into this classifying space. So we take a vector bundle given by this classifying map. So the classifying space construction is a functor, so we can apply it to this map G to O to get this vibration here. And a structure is as a lift to this BG, as a choice of lift. And so these BGs are, again, classifying spaces, but now for G bundles. So these vector bundles, stable vector bundles, stable G bundles correspond to homotopy classes from the base space into this BG. And so some examples of what these Gs are, you have a sort of special orthogonal group, spin, unitary, this kind of stuff. And so you can kind of organize these into a picture here in this kind of way, since spin is sort of the cover, universal cover of SO. And I've kind of, we'll come back to this picture, but this is sort of where we're headed, is we're kind of filling in some more of this picture with these covers of U and looking at structures that correspond to this. That's how we're going to define our U alpha-bordism.
Sorry, Jayden, am I supposed to know what all of these letters mean?
So these are sort of classical Lie groups. I guess it's hard, you know, there's only so much I can sort of jump into. I mean, SO, like the special orthogonal group, it's with rotations and things. So I guess I will say, you know, an SO structure just corresponds to an orientation. So yeah, it's not too important maybe, but just know that there are these groups, these Lie groups or topological groups, and structures correspond to the kind of normal things that you might try and put onto a manifold, a structure like a spin structure or orientation. So for U, this is going to correspond to, I guess it's called like an almost complex structure. So it's not a complex structure in the sort of, you know, geometric sense. It's sort of a topological definition where you don't require this integrability condition. Yeah, I hope that somewhat answers your question. Yeah, so these are just sort of structures that we've seen on, and I guess so far this is kind of defined for bundles, but if we want to talk about a G structure on a manifold, we really just mean putting this kind of structure on the tangent bundle of the manifold, the stable tangent bundle in this case. Okay, so I guess we have this idea of having different vector bundles. How do we distinguish them? We need some kind of invariance to sort of tell them apart. And these come in the form of characteristic classes. So I guess some of the sort of classical ones are these Stiefel-Whitney classes. And the way that you get them is, so we've just said that if we have a vector bundle, say on a manifold, this corresponds to a map from M to BO. But I mean, cohomology is a contravariant functor, so we can just take the sort of mod 2 cohomology and we get a map going back the other way. And we just look at basically the generators in this cohomology here. These sort of universal Stiefel-Whitney classes will correspond to the Stiefel-Whitney classes of our manifold just by pulling back via this classifying map. So maybe the details aren't so important, but there's these sort of characteristic classes that you can get from this classifying map. And similarly, so this was for unoriented bundles, so we have maps to BO. If we have, say, a stable complex structure by a map from M to BU, we can play the same kind of game with the integral cohomology and pull back these integral cohomology classes of BU, which are called Chern classes. And so these just give us invariance of, you know, unoriented bundles or complex or stable complex bundles, things like that. And actually, there's a connection with these characteristic classes with these just putting G structures on a bundle in the sense that so W1, the first Steeple-Whitney class, is an obstruction to orientations, so SO structures, meaning that you have this, say, a manifold. It has a certain Steeple-Whitney class. You can calculate the first Steeple-Whitney class, and that vanishes if and only if that manifold is orientable. Similarly, W2 is the obstruction to a spin structure, and C1 is the obstruction to an SU structure. Given, I guess you have to be a little bit careful about kind of what you're starting with, but the point being that these characteristic classes are useful to look at whether you can put certain structures on manifolds or not. Are there any other questions about anything so far?
So we're always just talking about tangent spaces, right?
Yeah, so you can play this game either with like the stable tangent bundle or with the stable, normal bundle. It turns out that they're equivalent, but it doesn't hurt to just think about the tangent bundle for pretty much anything, anytime I mention a manifold.
But I thought, like, on the Steeple-Whitney classes, like if you're talking about orientability, or if you're talking about spin structures, you're really talking about like sections of tangent bundles, aren't you? Like,
yeah, as in, like, if you're talking about the Steeple-Whitney classes of the manifold, I'm talking about the Steeple-Whitney classes of the tangent bundle of the manifold.
Yeah, okay. All right. Oh, so you're just sort of using them as examples, I suppose. Like,
yeah, I mean, so this goes for all vector bundles. You can do this game with all vector bundles, but often we care most about manifolds. And when we talk about the Steeple-Whitney class, say, of a manifold as opposed to a bundle, we really mean of the tangent bundle.
okay, yeah. Thank you.
No worries. Okay, so cobordism. So I guess we care about manifolds, but studying them up to sort of diffeomorphism or homeomorphism is really hard, impossible in some sense. And so we sort of have this coarser equivalence relation given by cobordism. So the idea is on the left here, we have this on the boundary, this sort of disjoint union of two circles. And on the right, we have a single circle. And we have this equivalence relation where these two manifolds are Borden or cobordant if there's a sort of one dimension higher manifold which bounds them or bounds their disjoint union. So in this case, you see this pair of pants sort of connects them all together and exhibits them as the boundary. And so you can sort of use this equivalence relation on n-dimensional manifolds, and you get a group, or the Bordism group, under disjoint union. And you can also play the same game with these G structures. So instead of just thinking of unoriented manifolds, you might think of, say, oriented manifolds, and then you require the sort of connecting manifold, the cobordism, to have an orientation as well that's compatible with the boundary. And same with stable complex structures and all of these structures, you can play the same kind of game. And so for a lot of these groups, these kind of groups I had before, the SO and U and these Lie groups, there's some classical results about computing these Bordism groups. I guess in this case, I've written it as a ring. It turns out that it also has a ring structure that you can multiply. You just take the product of two manifolds and you get a ring structure on Bordism. And so I guess the classical result is this Milner-Novikov calculation of the complex cobordism ring. And it turns out to just be a polynomial ring over the integers with generators in even dimensions. So I guess in terms of concrete groups, this means that all of the odd groups will vanish, and all the even ones, it'll have to do with the number of partitions, because you kind of sort of different ways to build up to sort of 2n using your generators, coupling them together kind of thing. Anyway, I guess it's not too important, but these are sort of classical results about these other bordism rings. So now I guess a quick detour. We'll talk a little bit about Thom spaces, because this is going to give us a way to actually calculate these bordism rings. So a Thom space, if you take a vector bundle, you can think of a Thom space as kind of a twisted suspension of the base space, where the twisting is kind of given to you by the bundle sort of data. So if you start off with a trivial bundle, then your Thom space is literally just the k-fold suspension. So suspending meaning like we cross it with, say, an interval and then collapse the ends. And so, yeah, this is in general, this Thom space is kind of a twisted version of this. Okay, and another quick word, I guess there's a lot of random things I'm throwing here, but spectra, if you haven't seen them before, the idea of spectra is that you have this category where it's kind of like spaces, but it kind of captures the stable information. And so there's a lot of the same tools you can use as investigating like topological spaces. You can take the cohomology groups of spectra, homotopy groups. You get these same kind of results from homotopy theory, like Whitehead's theorem, Gravich theorem, things like this. But it's quite nice because it's very algebraic. Like they form an additive category, these spectra, so you can add maps and things like that. Like have slightly nicer properties. And I guess the key point, the reason we care about spectra is if you take a G structure, so I said you have these BGNs, so B n minus 1, BG, and so on. And we have all of these universal bundles, which were the things that we used to pull back to get all of our generic bundles. And so you kind of have all of these ends, and what you do is you take the Thom space of each of these universal bundles, and then you use this spectrum kind of object to stabilize, because we kind of want to work stably, and spectra are kind of precisely the object that kind of is useful to capture this stable information. So yeah, so we get this Thom spectrum. It's basically just this kind of homotopy theoretic object that captures the information of the Thom spaces of all of these universal bundles. And the kind of amazing thing is that it has this very strong link with bordism. So we get this Pontryagin Thom isomorphism, which says that if you play this game where you have n-dimensional manifolds and you consider them up to sort of bordism, and you have these G structures, and you kind of do this whole thing, and it gives you, I mean, this is a very geometrically defined thing. It's almost like a combinatorial thing where you kind of are trying to work out if this combination of manifolds could bound and things, and yet it has this description by this very algebraic sort of homotopy theoretic object, the Thom spectrum. So in order to calculate this sort of difficult geometric thing, we kind of move over to the homotopy theory world and just calculate the spectrum. And then we kind of get this sort of crazy geometric information for free. So, homotopy theory. Okay, so I think that's it for the background. I know that was kind of a bit of a rush through some different things if you haven't seen it before. Were there any other questions to do with the sort of background?
I feel like it might be worth saying something about what the homotopy groups of a spectrum are. It's probably not something that people have seen. Yeah,
so I guess it's hard, how much to go into the definition of what these spectra are. I guess, the idea is maybe a good thing to keep in mind with the spectra is if you take a space, then you can take the suspension spectrum. So it's kind of a spectrum version of a space. And in that case, the homotopy groups are exactly the stable homotopy groups of the space, right? So if you heard of like stable homotopy groups of spheres, You might care about those. Normally, you'd have to sort of, do this kind of high n plus k of sk kind of business, and then make k high. This kind of stabilizes for you, and this ends up just being the nth homotopy of the suspension spectrum of the sphere. So, I mean, without going into the definition of how you actually, define these spectra, whether it's via, I guess I don't want to say too much more about, does that sort of answer the question, Eva? Yeah, I think I gave a kind of a run through of this, a practice run through, and I'm pushing it for time, so I'm trying to sort of be as economical as I can, but still hopefully get some kind of idea across. Okay, so these U alpha structures. So I guess I showed this picture before. We have this kind of, we had these as orientations, and then we had these sort of stable complex structures. So the way that spin comes up is that the fundamental group of SO is Z2. And so by sort of covering space theory, there's this universal double cover spin. And so we use that to lift to get our sort of spin structures. But we can play the same game with this stable unitary group. So the fundamental group of U turns out to be Z, the integers. And so the covers correspond to subgroups of Z. And so we get this sort of n's worth of covers, which we call the alpha fold cover, we call U alpha. And so given this sort of G structure, a U alpha structure is precisely a lift from. So if we start with, say, a stably complex manifold, stable complex structure, then a U alpha structure is a lift over this sort of B of this covering space. And so we were saying that sort of G structures often have characteristic classes that are obstructions, and this has one as well. The obstruction to putting a U alpha structure on a manifold is, or on a stably complex manifold, is the first Chern class mod alpha. And so in this sense, these U alpha structures sort of interpolate between a complex structure and an SU structure, since for an SU structure, you need it to vanish, the first Chern class to vanish entirely. Here, we just need it to vanish mod something. Okay, so some people have thought about this kind of U alpha bordism before, and we have some sort of partial results. So it was calculated that by Hearn in 2004 that rationally these U alpha bordism groups are just the same as complex bordism. And so really what this is saying is that any sort of interesting information is going to be purely torsion. And then back in the 60s, Stong had a look at the alpha equals 2 case pretty extensively, and found that the n bordism of n-dimensional U2 bordism is just n-dimensional SU bordism, direct sum with some free abelian group. And so I guess our plan is to try and calculate this integrally for all alpha. How are we going for time? I guess I'll quickly mention this sort of construction. This is sort of construction that's very useful. It turns out that the answer is only going to depend on the parity of alpha. So U alpha bordism or the associated Thom spectra, it only depends on whether alpha is odd or even. And that's kind of the main tool to show that is this Geiger-Chiarinella construction. So the idea is, given any stable complex structure and cohomology class in the second integral cohomology, you can sort of modify a stable complex structure without changing the underlying oriented vector bundle, but changing the first Chern class by any sort of even class. And this sort of 2 here is sort of indicative of where this sort of dependence on only the parity comes in. So maybe I don't want to say too much about this. Yeah, so I guess we showed that this Tom spectrum, this mu2 beta plus 1, so for odd alpha, turns out just to be homotopy equivalent to mu, the spectrum for just regular complex bordism. And so I guess from the Pontryagin-Tom isomorphism that we saw, that means on taking homotopy groups, you get that the bordism groups are just identical to the complex bordism groups. And so the idea of the proof is that you sort of take the universal U2 beta plus 1 bundle. So this is, say, a bundle over BU2 beta plus 1. And it's classified by a map to BU since it's a stable complex bundle. And you can do this Geiger-Chiarella. So I guess one thing to note is that the first Chern class of this guy xi is 2 beta plus 1. And so we can sort of play this changing the first Chern class by an even amount to get rid of this 2 beta, and we get a new a new stable complex bundle whose first Chern class is exactly 1. And then this is classified by a map to BU again because it's still a stable complex bundle, and we show that this is a homotopy equivalence. And then we sort of transfer this to the world of Tom spectra. So the details aren't too important. I just wanted to sort of maybe give a bit of a flavor of how you would sort of tackle this kind of problem. And then for the even case, it's a bit more complicated. It's the mu2 beta turns out to be homotopy equivalent to the wedge of MSU, so the Tom spectrum for SU, wedged with the double suspension of mu, so the complex Tom spectrum. And hence you can sort of take homotopy groups here and get this relation or this definition or this calculation for the U2 beta bordism, because this wedge here we're in an additive category with spectra, and so this wedge, it's a co-product, but it's also a product, and the homotopy groups play nicely, they just split. And another property of spectra is that this suspension in terms of the homotopy groups is pretty harmless, it just shifts left and right, and so we just basically get a shift by 2 of the bordism groups. Okay, so we've sort of calculated these U alpha bordism groups, but I guess there's a question of maybe why are we interested in these guys? So I guess one reason is a U2 structure, so this alpha equals 2 case, is exactly a simultaneous spin and complex structure. So if you care about sort of spin structures on complex manifolds, this is kind of a natural thing that would come up. And then these U alphas sort of generalize and interpolate between this U and SU, as I sort of said before. I mean, they've been investigated before by other people, which is always nice that sort of other people maybe care about this stuff. And I guess most concretely, these bordism groups arise in this sort of contact setting. It turns out there's this obstruction, this bordism obstruction to Stein fillability of almost contact manifolds, and it lives in a group which is related to these U alpha bordism groups. Okay, so I guess, are there any questions? Anything?
Actually, what's an almost complex structure?
Yeah, so I've kind of skirted around it a little bit, but I kind of mentioned before that if you have a real complex structure, say on a manifold, like a proper complex structure, say on a manifold, there's this integrability condition, which is not particularly topological, and an almost complex structure is just the sort of topological part of that. And then there's a similar game with contact structures. There's an almost contact structure. So a contact structure is a sort of hyperplane distribution of the tangent bundle of a manifold with this certain complete non-integrability condition. And that kind of complete non-integrability is this kind of maybe slightly geometric condition, and the topological version, this sort of almost contact structure, is just not worrying about that. It's just the topological part. Does that answer your question?
I think so. So are you considering these two these distributions up to some sort of homotopy where it's allowed to break the non-integrability somewhere, basically? Or
yeah, I think that's fair. I got to admit, my knowledge, especially on the sort of the proper geometric contact stuff, is pretty minimal.
okay, yeah, no, that's all right.
The fact that mu 2 beta plus 1 is a homotopy equivalent to mu have anything to do with bot periodicity? Like a priori, it doesn't seem like it should, but the fact that it's 2.
Yeah, no, it's a good question. I see where you're coming from. It is sort of, an interesting connection there. That's sort of the 2 periodicity. It's not something that I've thought of before. I don't think so off the top of my head, but
Well, don't let it derail the talk. We can talk about after.
yeah, no, it's an interesting question. All right, so I guess moving on, this Stein filling obstruction. So yeah, I guess I was saying these kind of this sort of geometric definition of a contact structure by these hyperplane distributions come as either over twisted or tight. There's this kind of 2 types, and sort of one of the tightest sort of kinds of contact structure you can get is one which is Stein fillable, which means it comes as sort of the boundary of a Stein domain. And then we have this kind of almost contact structure that I was talking about, this sort of topological version, which is defined here. So the precise definition is, it's set up in the same as this sort of G structure formalism, where you have, say, an oriented 2q plus 1 manifold, which is given by this. So now we're not working stably. And an almost contact structure is precisely just a lift from here. There's a natural map. And this gives you an almost contact structure. And anytime you have an almost contact structure, you can you get this map M from M to BUQ, and you can stabilize that by just composing with this map to BU. So you get an associated stable complex structure. And that's kind of where this relationship with U alpha-bordism is going to come in. So I guess a question you might want to ask is, when does one of these topological almost contact structures come from a sort of honest geometric contact structure? And due to sort of fairly recent work by Borman, Elishberg, and Murphy, if we care just about over twisted structures, say, then it turns out it's always the case, sort of H principle thing. But for tight structures, it's as far as I know, not clear whether these always come from these tight contact structures or not. And so I guess one question you might ask is, you pick a specific type of tight contact structure, which is a Stein fillable one, and say, okay, well, is a given almost contact structure Stein fillable? And this is sort of the question that Bowden, Crowley, and Stipschitz sort of tackled. And they had this theorem which says that, so it's a sort of a big slab of text here, and I've highlighted some words that I haven't defined yet, but we'll kind of come back to it in a second. But the idea is, if you're given sort of a closed almost contact manifold, then you take the associated stable complex structure, and this has this sort of invariant, which is called a complex normal K-type. And then somehow from this complex normal K-type, you get some kind of associated bordism group, and the bordism obstruction to Stein fillability lives in this bordism group. So I guess I'll kind of define what these invariants are, and then we'll kind of circle back and have another look at this theorem. So okay, what are complex normal K-types? So let's say we have a stably complex manifold. What we want to do is we want to take the Moore-Postlenkov factorization of this map. So If you've seen like Posnikov towers, or Posnikov theory of a space, this is kind of a version just for maps. And the idea is that, you want this map, you're kind of taking your classifying map, so M to BU, and you're making it so that the maps sort of roughly up to K are isomorphisms on homotopy groups for this map, and sort of roughly above K, you get isomorphisms on homotopy groups for this map. And it turns out that this map on the right is unique in some sense, and we call that the complex normal K type. And so given a stable complex structure, you get this as sort of an invariant of that stable complex structure, this complex normal K type. And hopefully this picture looks somewhat familiar, because this is exactly sort of the G structure picture that we set up, where you have your map to BU, and then we have a fibration coming down here, and then we're looking at lifts here. So you can picture this map here, which we call a K smoothing, as sort of picking a BK structure on your stably complex manifold. Okay, so I guess sort of circling back to here, what have we said? We take a closed almost contact manifold, we take the associated stable complex structure by just stabilizing. It has this invariant from the Posnikov factorization, the complex normal Q-1 type. And then we want to, this was sort of a G structure. So you get these sort of G-bordism groups. And we want to sort of look at whether an element in there is trivial or not. And so I guess this was the work of as I said, Bowden, Crowley, and Stipschitz. And I guess what I was interested in that maybe is if we look specifically at, say, dimension 5. So in this case, Q equals 2. What can we say about 5 manifolds? And so if we have a 5 manifold, we need the Q-1 type, complex normal Q-1 type. So we need to be able to say something about what complex normal 1 types look like, and then what their bordism theories look like. So I guess what goes into this sort of complex normal 1 type, whenever you have a stable complex structure on a manifold, you get this invariant, which we call alpha. And it can be described in 2 ways. You can either describe it as the divisibility of the first Chern class of the universal cover of your manifold, or you can describe it as, you have, as always, this classifying map for a stable complex structure, and you just take the induced map on pi2. So you get a map from pi2 of M to pi2 of BU, but pi2 of BU is isomorphic to Z. And so you look at the image of this map. And so this is, strongly related to the first Chern class. The index of this image is going to be our alpha. And so I guess our result is that there's sort of this classification of complex normal 1 types. So the complex normal 1 type of a stably complex manifold M is either a BU, BSU, or BU alpha fibration over this K pi 1. So this is an Eilenberg plane space. It's basically a space with the property that the only non-trivial homotopy group is the first one, and that has this group as the fundamental group. The details aren't too important. It's just some space which depends only on pi 1 of M. And the sort of invariants that sort of determine what your complex number 1 type are precisely the fundamental group of M, since that gives you this K pi 1. The invariant alpha, which is going to sort of determine which of these 3 cases you're in, and specifically which alpha here. And also a twisting class, which is in the cohomology of this K pi 1, which basically tells you what kind of fibration you have, like how it's twisting. Moving on for time. Still got a little bit. Okay, so maybe I'll come back to this in a second. So I guess now we have these complex normal 1 types. So if we're looking at 5 manifolds, we're kind of primed to say something now. We know what the complex normal 1 types look like, and it turns out they're related to these U alpha bordism groups, but we calculated those. So Okay, what's our takeaway? So I guess the first thing we can say is that we have a new proof of the theorem of Gygas, that every almost contact structure on a simply connected 5 manifold is Stein fillable. And so the reason for that is, well, as we said, the complex normal 1 type of your manifold is precisely a BU, BSU, or BU alpha fibration over this K pi 1. But if you're simply connected, then this pi 1 vanishes. And so this is just like a contractible space. And so this fibration ends up just being BU, BSU, or BU alpha itself. And so we just end up with literally on the nose complex SU or U alpha structures as this bordism group. And we've already calculated these, right? So we know that the 5th U, 5th SU, and 5th U alpha bordism groups, these all vanish. So these first 2 are sort of classical results, and then this comes from our calculation of U alpha bordism. Since all of these vanish, the group where the sort of obstruction lives in vanishes, and so the obstruction has to vanish. And then I guess here I've kind of got this big long theorem here. I mean, what this is really saying is it turns out that there's a spectral sequence which you can use to sort of analyze this relationship called the James spectral sequence when you have sort of 2 bordisms related via a fibration. And basically you can sort of write out this, this spectral sequence, and this statement here is just sort of the simplest statement you can make, which is you look at the E2 page, it depends on some homologies of your fundamental group. If these were to all vanish, then your spectral sequence would immediately collapse and your group would be trivial. But I guess the hope is, because we've sort of analyzed these spectra, you know, you can not necessarily make a general statement, but if you were to give me an almost contact manifold, the hope would be that you could sort of go away, look at the spectral sequence, and perhaps analyze the differentials in that using the structure of these Tom spectra, and be able to say something about you know, which differentials, you know, what the differentials are doing, and hence what group you're converging to. So I guess that's just maybe for people who have seen some spectral sequences before. And so I guess circling back to this example, there's this sort of twisting class, but if the first Chern class of M tilde and the first Chern class of M are equally divisible, in some sense, the twisting class measures the difference between the divisibility of the first Chern class of M and its universal cover. And so if they're equally divisible, the twisting class vanishes, and so you get a trivial fibration, so you just get a product. And so it turns out that in this case, the bordism obstruction lives in just the U alpha bordism of K pi 1. So in bordism theories, this is sort of singular bordism with maps into this guy. And this can be analyzed via an Atiyah Hertzbruch spectral sequence, if people have heard of that. So yeah, I think I'll stop there. That's sort of pretty much everything I wanted to go through.
Awesome. Everyone, let's give Jayden a big thank you.